a couple problems. I did a couple problems. You had a handout that we did this problem. Um, the whole concept of if separation of variables, separation of variables, is you take the equation and you replace y prime with dy dx, and then you separate the terms that involve y and dy on one side and x and dx on the other side. So we're just going to work this problem kind of as a second effort at doing separation of variables. So it's the first thing in your sheet, and I don't think Zane doesn't have one, so this is yours. Oh, you do have one of them. No, you don't. You don't have one of them. And if you didn't bring it, I'll write out the problem for you. You can write on a separate piece of paper. So the differential equation is y times y prime minus e to the x equals 0. The initial condition is y of 0 equals 4. And you replace, the first step is to replace y prime with dy divided by dx. And then once you do that, then move the stuff that's involving x to the right-hand side, multiply both sides by dx. Once you do that, you will have the y stuff on the left-hand side, the y and the dy, and the x and dx, and then you integrate both sides separately. And because the left-hand side will be a function of y, you integrate just as you normally do. There's no mixing of variables. The same with the left-hand side. Once you've integrated it, you have one arbitrary constant, and then you'll use the initial conditions to evaluate that arbitrary constant. So you can see at the top, I've separated the variables. I've got y times dy on the left-hand side. and e to the x times dx on the right-hand side. So that means you can integrate each side using the techniques for integrating functions of one variable. This function is of the variable y. This is the function of the variable x. So you add 1 to the exponent divided by the new exponent. The integral of e to the x is just e to the x. And you add your one arbitrary constant. So this is what we call the general solution, because there are a series of solutions that are only separated by a vertical displacement. So which one of those curves is determined by the initial condition. So this is your x value, so you're going to put x equals 0 in there, and y is the value you put in for y. And you don't have to explicitly solve it for y. So then so you do that, and you solve for c. So this is what we call the general solution. So once you figure out the arbitrary constant, then you just plug that back in to your general solution, and that is called your particular solution. And you could solve explicitly for y. You'd end up with two solutions because you'd have plus or minus. Let's just do the algebra for the heck of it. So if you multiply both sides by 2, you'll get y squared equals 2 e to the x plus 14. And take the square root, you get y equals plus or minus the square root of 2 e to the x plus 14. You got to remember both solutions there. And let's program. And we're going to do a two-dimensional plot. And the equation is, we can do the implicit version, which would be y divided by 2 equals e to the x plus 7. Let's see what that does. So there it is. That's not the entire solution. That's just the part that I got initially. So let me let's do this. That didn't work. Okay, let's try it again. Equation, implicit. Okay, so that's the solution. I think if you did the explicit solution, y equals, what did we have? We had the square root of the e to the x, or actually it was 2 times e to the x plus 14. Okay, let's see what that looks like. The same. You don't see it because it's written over. It drew over top of one of the existing curves. So you just have to. The top curve would be plus the square root, and the bottom curve would be negative the square root. Okay. So that's another example of separation of variables. Now, there are some differential equations that are not initially separable to x and y, but can be made separable by using a transformation. So transformation is just defining a new variable that has some relationship to the old variables. And as long as you transform it correctly through each term, the equations are equivalent to each other. Um, and what it allows you to do is the transformed equation is separable. So then you solve the separable equation in the transform variables. Once you've integrated, then you can substitute back in to find the solution in terms of the original two variables. And the kind of equation that does that are called homogeneous functions. So what is it? How do you tell if a function is homogeneous? Well, what you do is you do what's on the right-hand side, is you evaluate the function, but not at x and y, but at t times x and t times y. So you just some factor t. It's not a specific t, it's just a number. 5, it could be 5 or 2 or 3 or whatever. And what you'll find out is once you plug that into the original equation, it'll be the original equation times t raised to the n power. So let's just look at let's look at an example of an equation is homogeneous. So this is a homogeneous equation. It's not a homogeneous differential equation, but if it's a homogeneous differential equation, then it's a homogeneous equation. So f of x, y, meaning it's a function of both x and y, is x cubed minus 4x times y squared plus y cubed. Verify that it is homogeneous. So what you do is you take the original equation, and for x you substitute in t times x, and for y you substitute t times y. So let's plug that in there. So we're going to do f of tx and ty. What that means is we're just multiplying them together. So for x I put in tx. So you can see I'm taking the original equation. I'm substituting for x, I'm putting in t times x. And then for y, I'm putting in t times y. And then finally for y, I'm putting in t times y. Now the properties of exponents say if you have two things multiplied together and raise them to a power, it's the same as each term in the product raised to the power separately. So because I have tx cubed, it's the same as t cubed x cubed. This one's not affected because it doesn't have, it's raised to the first power. This one's squared, so you get t squared y squared, and then finally you get t cubed y cubed. And you'll notice that each term in that expression has t cubed. So we have t cubed, we have t times t squared, which is t cubed, and we have t cubed. So you can factor out the t cubed. So we factor out the t cubed. What we have left is x cubed minus 4. We have an x, and we have a y squared, and we have a y cubed. So this is t cubed times f of just xy. So original function was just a function of xy. So that satisfies the requirement for it being a homogeneous equation. In this case, n is 3. You can kind of think of it like physics, where you have units, and if the units were meters, you'd end up with meters cubed for all of the expressions. So it's kind of that. If I replaced, say in the second term, I had negative 4xy instead of y squared, then it wouldn't be homogeneous anymore, and I couldn't separate it. So again, from a unit standpoint, if you think about this, you'll notice in this case there's really nothing. The only thing that have to have the same units would be x and y. You have x squared, y squared in the denominator. You have to add those together to be compatible from a unit standpoint. That would be one way to look at it. We could use this technique. Why don't you just do that? So go ahead and plug in, evaluate f of t times x and t times y, and verify that it is homogeneous. They don't have to the t's don't have to cancel out. You just have to be able to factor out a common, the same amount from each. Well, yeah, this one's not, like I said, there's not 3 terms like the previous one. It's just really one numerator. So you square t times x, it's t squared x squared. Same for this one. Denominator, same thing. You've got t squared and t squared, it's 2 to the 4th. And then you put these two together, x squared, y squared, which is in the original equation. And here you've got t squared. So when you take that outside the square root, you get t. And then t to the 4th over t is just t cubed. And so we've got t cubed times the original function. It's just a coincidence that it's t cubed. Doesn't have to be t cubed. Okay, so that's how you determine whether something's homogeneous or not. So once you've done that, you can make this substitution. So if an equation is homogeneous, then it can be transformed into a differential equation whose variables are separable by the substitution y is equal to, and that symbol is not v, it's called nu. It's the Greek symbol that looks like a V. So I'm just going to show you how this. So it looks like kind of like that. Let's look it up. Let's look it up on Google. Show you the official one, since I'm not greatest drawer in the world here. So if you put in Greek nu, so there it is. So it looks kind of like a V, really. Capital nu is N. A small nu looks like a V. So if you use a V, it's okay. I'm not gonna. If you don't do a perfect job of drawing a nu, don't worry about it. So there's 2 things you've got to substitute though for. You don't substitute, which for y you can put in nu x, nu times x. But the tricky part is dv, because we also have to substitute in for dv. So let's just and the way you do that is like we talked about in chapter 2, I think it was, of the concept of differentials. So let me just show you how that works. So the y substitution's piece of cake. But if you do dy, that's the same as the differential of nu times x. So I'm just substituting nu times x in there, but because this is a product, you have to use the product rule. So what you get is nu times dx plus x times d nu. So you take the derivative of the second term times the first term plus the second term times the derivative of the first term. So this is the product rule applied to a differential instead of to a variable. So remember, the product rule says if you want to take the derivative with respect to x of f of x times g of x, it's equal to f of x times g prime of x plus g of x times f prime of x. So that's how you get that. So those are the substitutions that we're going to make. So we have this substitution and we have this substitution. And once you make those substitutions, an equation that is not initially, if it's a homogeneous equation, it's not initially separable, it will be separable when you make those substitutions. So let's look at an example. I'll come back to that in a second. Okay. Yeah, this is good. Well, that one's more, yeah, let's just do this one. This one's easier. So you can kind of see that it's a homogeneous equation because if I substitute t times x and t times y, I'll be able to factor out t's and they'll cancel each other out. But if I tried to separate it, let's just try to separate it and see it doesn't work. Okay, so let me take the option 1 off for right now. You know, you might not initially recognize it as not being separable, so we might try to do this. So we'd say, okay, we have we change y prime into dy dx. So let's see, how do I get the y terms on one side? You could see, well, I could multiply both sides by dx. That would give me x plus y times dx. And I could just leave the 2x over here. The problem is, as you can see, is that I've got this y. I've got this y, and there's no way that I can get it on the other side. You could try, but it's not going to work. Okay, so it's not separable. So you can't use separation of variables. But you look at it and you say, well, it's not separable, but it is a homogeneous function. So that means I should be able to use this substitution to solve the problem. So we still change y prime into dy dx. And then we're going to multiply both sides. We're going to cross multiply. So we'll get 2x dy equals x plus y times dx. So you want to get everything on one line. So if you've got a differential equation that involves a division, which happens a lot of times with the homogeneous equations, you want to get it all on. You want to eliminate the denominators. So you can do that by cross multiplying. Okay, the substitutions I have that y equals nu x and dy is equal to nu dx plus x d nu. Okay, so let me just write the substitutions in here. So I've got 2x, my original equation, 2x times dy, which dy is nu dx plus x d nu. And then the right-hand side of the equation, I've got x plus y, but y is equal to nu x. And dx just stays the same. So you can see I've made this substitution here, and I've made that substitution there. So step one is get everything on the same line. Step 2 is make the substitutions. Okay, let's multiply everything out. So we're going to distribute this 2x to those two terms. So you get 2x new dx, 2x new dx, plus 2x times x, so that's 2x squared d new. And then on the right hand side we've got x times dx, and then new x times dx, plus new x dx. Or I guess x new d new. I guess, yeah, let's put the x first. So it's 2, it's going to be x squared new. I don't have x squared, I just have x. I don't know why I did that. Fix that. Okay. That's the hard part about these, just the algebra. So x new dx is the same right there. Okay. Now, a lot of times you can do some simplification. So once you've multiplied everything out, you see if I can combine terms that have the same expressions. And in this case, I do right here. So you have 2x new dx, and I have x new dx. So those are like terms. They look, there are a lot of parts of it, but they are like terms. So what I can do is if I subtract x new dx from both sides, I can eliminate one of the terms. So let's do that. So what we're going to do is we're going to subtract x new dx from both sides. And what that leaves me with is, on the right hand side, is I have 1x new dx plus 2x squared d new is the next term. The right hand side is x dx. This term's eliminated. Okay, next thing you do is move terms with dx to one side and terms with d new to the other. So I've got dx here, I've got dx there, so I'm going to move this over there, and I'm going to move that to the other side. So I'll have x new dx minus x dx. So that's this going to the other side becoming negative, and then this one goes to the other side, becomes negative. And there was one additional simplification that I missed out on. Does anybody see what I could have done here, even before I moved them? Do they have a common term? So here are their common terms. Yes. The other one is a lot of times you end up with an extra something in there. So this one had an extra x. So if I could simplify it a little bit further by dividing by x. And I should have done that earlier, but it's okay. So what we're going to do here is we're going to divide both sides by x. So that leaves me with new x minus dx equals negative 2x d new. Okay, now the next thing we can do is you can factor out the dx. So if we do that, we'll get new minus 1 times dx on the left-hand side. And on the right-hand side, there's nothing I really can do because I've only got one term. Okay, now separate variables. So I can divide by new minus 1, and I can divide by x. So we divide by new minus 1 and by x. So that leaves me with dx divided by x is equal to negative 2 divided by new minus 1 d nu. So this goes down there. This goes down there. What I'm going to do is take this negative sign and just flip it around here. So I'll have dx over x is equal to 2 divided by 1 minus nu instead of negative nu minus 1. So now I've separated the variables. So that's the whole purpose of what we just did. So let's review what we do. First you have to determine that it's homogeneous. Once you do that, you substitute dy dx for y prime, if it hasn't already been done. Then you make the substitutions. Well, actually, you get everything on one line. So you get rid of any fractions. You make the two substitutions. Multiply everything out until you get all separate terms. You get rid of all the parentheses. You try to simplify it by eliminating or combining like terms, dividing by a common term, and then you separate the equations. And ultimately, you should get someplace where you've got a new equation in the two new variables that are separable. And at that point, you can integrate. So now we're going to integrate. So you'll get the integral of dx over x. You'll get the integral of 2 divided by 1 minus nu d nu. The left-hand side is the natural log of the absolute value of x. The right-hand side is, how do you do that? Well, you can use u substitution. Let me just move this down a little bit. So you'd let u equal 1 minus nu. So du equals negative d nu. So this goes to 0. When you take the derivative, you get the negative sign. The derivative of nu is d nu, or is 1, and then you multiply by d nu. Okay, then you'd make the substitution. So you'd end up with 2 divided by u times negative du. So here what I'm doing is I'm saying d nu is equal to negative du. Another way to write that, just multiply both sides by negative 1. So you can see what you're going to end up with is you're going to end up with negative. The negative sign comes out front, so does the 2, and you end up with du over u, which is the natural log of the absolute value of u plus c. Then you have to substitute u back in. Lots of substitutions here. So you get the natural log of the absolute value of u, which is 1 minus nu plus c. And then finally, you could finally use original substitution, which was that nu, or y, was equal to nu x, or if you solve for nu equals y over x. So you plug that back in, you get the natural log of the absolute value of x is equal to negative 2 times the natural log of 1 minus y divided by x plus c. That's your solution. Okay, it's not easy. It's not solving explicitly for y. It's an implicit equation, but it's a solution. You know, it shows you can get a solution. It doesn't mean that the solution is simple or straightforward, but it is a solution. Okay, here's the good news. Okay. Well, the bad news is, yeah, you still have to do homework problems. Okay. The good news is you have my solutions. The good news is, so that's the good news, bad news, good news. Okay. You have to do homework. Bad news. I tell you how to do them if you get stuck. Good news. On the exam, basically I ask you to get to the top. I don't ask you to solve it, because a lot of times when you do these homogeneous equation solutions, they're pretty tricky, and so what I want you to understand out of this whole thing is that the whole concept of solving solving calculus problems a lot of times is making the appropriate substitutions and rewriting the equation in terms of variables that make the problem solvable. If you I don't remember seeing any homogeneous problems in my engineering training, so it's an interesting concept. I want you to try to understand it, but if you don't get all the little nuances here, you're like, I'd never get that. And it's probably true. But at least you kind of have a general idea of it is possible. And if you take differential equations class, you'll get more experience at doing this kind of thing. So the key thing here is what you need to know is how to go from here, which is a differential equation that's not separable, to here, where you have a differential equation that is separable. So let me go ahead and assign your homework here for this section for right now. There you go. We'll come back and do some more. We'll do another problem or two, but I just want to give you kind of an idea today. There is one more topic in this chapter, which actually has nothing to do with homogeneous equations, but that's what we're going to talk about next. That's why a lot of people say differential equations is the hardest math class they have to take, because you get into, fairly complex solutions. Okay, so let's okay, before we're going to talk, the second part of section 3 is talking about logistic growth. And logistic growth is like exponential growth, except you don't have an unlimited supply of food supply, if you want to talk about it in terms of animals. So as long as you have an unlimited supply, the population of something grows exponentially. That's what's happening to the human race at some point. But at some point we're going to run out of resources. So what happens when that occurs? That's interesting. But if you're talking about deer, let's say deer, as the number of deer increase, the food supply gets smaller, and at some point there's going to be competition for the food supply. And so what that does is it reduces the fertility of the deer, and they have less deer, or less deer survive, and the population levels off at some point. And that's the whole idea of logistic growth. But to be able to solve the differential equation associated with that, we have to use partial fractions, which you should have had in pre-calculus. So I'm just giving you a little review of what partial fractions are. So partial fractions are when you have this kind of an arrangement. You have a rational expression, 1 over x minus 1 times x plus 3, and normally you would see it multiplied out, but if you can factor the denominator into two terms, you can rewrite that as some constant a divided by one of the factors by itself plus constant b times the other factor. And the advantage of that is, we'll find out in chapter 8, we'll cover partial fractions again, but the advantage is I can't integrate the term on the left-hand side, but I can integrate the term on the right-hand side based on the equations that we have. So just it's another technique to get to a point where you have formulas that you can use. Here we have a linear term and a quadratic term. There you can break it up into a constant divided by the linear term plus bx plus c divided by the squared term. And again, you can solve this. That's the integral of, or the natural log of the absolute value of x plus 1. Here you can do it by breaking it up to this point, which is involves the natural log, and this one involves the arctangent. So those are, by using partial fractions, you can get those solved. Okay, so that's what partial fractions are. So if you look at the differential equation for logistic growth, well, what this is telling me is this is the equation, that was the differential equation for exponential growth. dy dt equals k times y. And what we did is we separated the variables and we integrated both sides, and then we did some manipulation, and the solution to this differential equation was y is equal to c times e to the k x, or t in this case because it's t. Okay, we use that equation. So that's the exponential growth. Now the differential equation for logistic growth is dy dt, same thing. The increase in y is equal to k, some constant k, times y. But you got this extra term. And what it's telling you is that when the population divided by what's called the carrying capacity. So L is the carrying capacity. That's basically how many organisms can be supported by the ecosystem. So maybe it's 1,000 deer, or maybe it's 20 billion bacteria. But at some point, they're going to start competing for resources. So when this population is small compared to the carrying capacity, this term basically, you ignore that term, and you end up with the differential equation at the top. So when you're first starting out in this kind of situation, the function grows exponentially. But at some point, when these get close to each other, where the population is close to the carrying capacity, then at that point this ratio will be 1, and you get 1 minus 1, which is 0, and therefore at some point the population growth is going to go to 0, and once it goes to 0, then it just levels out. So that's the additional term is to reflect the effect of competition and limited resources on the growth for population. So now we need to be able to solve, so we're going to solve this differential equation. Now you can actually solve it separately, because you can see that t is not anywhere except in the dt term. So it's kind of surprising that it's in the separation of variables section. But so we're going to take this differential equation and we're going to solve it. Solve the differential equation for y as a function of t using separation of variables. So if we divide, what I'm going to do is I'm going to leave the k on the right hand side. So I'm going to divide by y times 1 minus y divided by L. So I've taken these two terms, divided by both sides by it, and I've multiplied both sides by dt. So I get that. So that's my separable equation. I've got my y terms on the left-hand side and my t terms on the right-hand side. So obviously the left-hand side is going to be much more difficult to solve. To simplify things, I'm going to multiply both the numerator and the denominator by L. What that does is it'll get rid of this fraction. So I'll have L times dy divided by y times L minus y. So by multiplying here by L, this one becomes L, and here you get y over L times L, which is just y. And then the right-hand side is k times dt. So what we have to do is we have to use partial fractions to break this up. So we're going to do a little separate. We're going to do a separate partial fraction thing over here to show how we can rewrite this as two terms instead of one term. So let's add a page here and do the partial fraction stuff by itself. So what we have is we have 1 over y times L minus y. So I've got a linear term and then a linear term. So I can make this into a over y plus b divided by L minus y. Because I know how to integrate this. It's going to be dy over y. And I can also do dy over L minus y. I've just done that a second ago. So on another problem. So the way you do partial fractions is you, when you have two terms like this, you cross multiply to get a common denominator. So you'd have a times L minus y plus b times y, all divided by y times L minus y. The way that works is, you multiply the first term by L minus y over L minus y. You multiply the second term, b, by y divided by y, and then combine the two terms and get that expression. So then what you're able to do is you're able to say, well, I've got the same denominator, so the numerators must be equal to each other. And then what we can do is we can you can set y equal to any value to solve for a and b. And there are two choices. One, you can let y equal 0, or you can set y equal to L. And the reason you choose those is because if I let y equal 0, that makes b disappear, and all I have is a left to solve for. And if I let y equal L, that term goes to 0, and therefore I can solve for b easily. But theoretically, you can pick any value for y. You'd end up with two equations and two unknowns. The two unknowns are a and b, but you can make it easier by judiciously choosing y. Okay, so if I set y equal to 0, what will happen is I'll get 1 is equal to a times L minus 0. So I get 1 is equal to a times L, or a is equal to 1 over L. And then if I plug in y equal L, I'll get 1 is equal to a times 0. See, that goes to 0 when y equals L, plus b times y, which is L. So b is equal to 1 over L as well. So this original expression that had both had a product in the denominator, we can rewrite that as two separate terms. So that's going to be equal to 1 over L, which is a, divided by y, plus 1 over L times that. So that's the whole idea. The whole idea of partial fractions is to take this product of terms, linear terms in the denominator, and break it up into two separate expressions. Okay, so we'll continue on this on Thursday.